Hello, this is a video about the Qibec 1-bit 1-instruction transistor CPU that you can see here. Today we will be talking about the digital I/O latch or DIO latch, and it is this block right here inside the white rectangle. As you can see, this block shares one plug-in module with a display. This here is a general purpose microcontroller which serves as a display controller now. This is a row column LED matrix 16 by 16. It makes sense to have the display on the frontmost module obviously because you can see it then, but it doesn't make much sense to have the DIO latch shared on that module, so it probably, a subsequent version, it will probably move to another module, for example the timing module that you see here. It makes more sense to have it here, I think. It doesn't really make sense to have a separate board just for this. It's a bit waste of space. So let's take a look at what this module is. Actually, if you consider the whole Qibec CPU, there's approximately 32 bits going to a ROM, and there's 1 bit going to a RAM, connected to the RAM. So 32 bits are connected to the ROM, and 1 bit is connected to the RAM. The subcircuit inside the CPU that takes care of all communication to the RAM on the electric level is the DIO latch. So that's the only subcircuit of the CPU that's actually connected to the RAM. As you can see in another video, the addressing of the RAM is taken care of by the ROM. Right? And we will not go into that in detail here. First, in the previous video we showed how a set-reset latch could be made out of NAND-gates. Now the DIO-latch that we will be talking about in this video is not much more than a set-reset latch and actually resembles the 8-bit latch a lot, which is this module. Except it's 1/8 of that module basically. Can be made out of a set-reset latch and NAND gate, in the following way. Remember what a set-reset latch looks like and how it works. If you don't know how it works, please see a previous video where it is explained. Set-reset latch has a set, low active set input. If you apply 0 at this input, the output will go to 1. If you apply 0 at the low active reset input, the output will go to 0. Output Q overbar is always the inverse of the output Q, so there's that. In order to turn this into DIO latch, we can go about the following way. Take a NAND gate, another NAND gate, and connect it in this way. This is the data input. The data bit is input, and this is an enable input. The enable input copies the data bit to the output, so it enables the latch. It makes a latch transparent. Now, in the previous video, when we talked about the 8-bit latch that you saw just now, or rather 1/8 of that board, we drew a similar circuit. The difference between the DIO latch in this video and the 8-bit latch in the other video is that in this case we have an inverted output Q overbar in addition to Q, and this latch does not have a clear, while the 8-bit latch had a clear to reset it to the initial CPU state, because the block was that module was used to start executing at program address 0. In this case of DIO latch, we don't need that. So also in the previous video talking about the 8-bit latch, we used a truth table. Now in retrospect that may be not very clear, it doesn't tell you much about how this block works. So let's do it another way now. To see how this works, because these two are NAND gates, let's first look at what happens if the enable input is 0. So remember that, as you can see, the enable input only serves as the input of both NAND gates. So if you take any NAND gate with one input A and an output Q, and you apply a fixed 0 to one of the inputs, the output of the NAND gate is always 1. In other words, this is the same as having a constant 1 to apply to an input somewhere, right? So in case this enable input is 0, a 1 is applied at both of these inputs. In other words, this latch doesn't change state. So a 0 on the E input will not change any state, will not do anything, regardless of the data input. Now, I should have kept that there. In case the enable input is 1, I should have kept that there. Remember that a latch with input A and output Q, and one of the other, the other input is a fixed 1, behaves like an inverter. Output Q, input A. Right? So in case enable input is 1, you can replace this. You can forget the whole enable input and replace the NAND gates with 2 inverters. And in this case, you can see that if you apply a 0 at the data input, the set input will be 1, the reset input will be 0, because there is an inverter between the set input and the reset input. So actually applying a 0 at the data input will reset the latch, so it will cause a 0 at the Q output. Remember, this goes only for a 1 at the enable input. So if you apply a 1 at the data input, the set input will be 0, the reset input will be 1. These are always each other's inverse because of the inverter here. And because these two are low active inputs, a 0 at the set input will cause a 1 at the Q output. In other words, if the enable is activated, enable input, then the latch is transparent. So 1 at the D input will show up as a 1 at the Q output, and 0 at the D input will show up as a 0 at the Q output. So that's basically how it works. Now, this latch can be drawn like, well, let's draw it here, like this. As a D input, enable input. Actually, let's do it in red. D input, enable input, Q output, Q overbar output. For the sake of this drawing, I shouldn't have done that. Let's put Q overbar there. Let's put Q at the bottom. It's easier to draw. This is an output, this is an output, this is an input, this is an input. Right, let's draw the RAM, because this is the only subcircuit of the CPU that is connected to the RAM at the electric level. So all communication to the RAM takes place using this block, this subcircuit. Let's draw the RAM like that. Let's say RAM has an address input. We will not talk about the value of that address input, but it selects 1 out of a number of memory cells, right? So the RAM has a write input. In case the write input is 0, you can read data from the RAM, so the RAM will drive its output using a buffer. Let's draw it like that. Alright. In case the write input is 1, the RAM will not drive its output, but will read instead. So an external circuit can write to the RAM. Right? And remember that the CPU is in this cloud somewhere, right? So first let's look at what happens while reading from RAM by the CPU. So the CPU reads from RAM. Now it applies a 0 at the write input, because we want to read instead of write to the RAM. By doing that, the RAM enables its driver output, so it connects the driver output to put a strong voltage at this point. And let's say the binary value of that voltage is X at this point. Now whenever a pulse occurs on the enable input, or when the enable input is made 1, this X is copied to the Q output. Q output becomes X. Q overbar input becomes the inverse of X, of course. Now we then remove the enable input from the latch, the output stay put, because the latch has remembered its input and latched it on the output. So, that we're reading from RAM. To write, we can apply 1 at the RAM's write input. By doing that, we disconnect the driver from the RAM. Now, this would not work because at this point this node has no circuit driving it, so this would be floating. Instead, what we do is having a resistor connected from the output, the inverted output of the latch, back to the input. Now remember, the enable input is 0, so this latch doesn't copy its input to its output. This output is the inverse of its previous input, right? So this was the inverse of that X, which is no longer there. Because no circuit here is driving this node, because the driver is disconnected, the inverting output of the latch is weakly driving this node. In other words, the voltage at this node will be the inverse of X, and the one driving the node right now is the latch itself. Alright? And the RAM will see the inverted value of X, so the inverted value of the previous value at the input, and will latch it itself. And that's basically how it works. So the operation of the CPU, for details please see another video, but the operation is first the DIO-latch reads a value from the RAM. It doesn't matter which address, someone else addresses the RAM, latches it, so the Q output becomes the original value. Then it will enable the write input of the RAM, thereby disconnecting its driver, so that this weak signal, weakly coupled by this resistor into this node, will drive this node, and then the RAM will see this value. So that's basically how it works. Now in the context of the whole CPU, this signal will eventually come from a clock line. The clock signals within the CPU will be discussed in a video of its own. It's not discussed here. This node here, oops, this output Q will go to a multiplexer select input, and this output Q will basically be used to choose between an optional next address and the current program counter incremented by 1, which is also the subject of another video. It's not discussed here. So that's basically how it works. So for the whole CPU, the part interfacing to the RAM is the DIO-latch, the digital I/O latch, which looks like that. That resistor is actually there, it's a real resistor, it's on the board. And yeah, that's how it works. So let's look at that on the breadboard. I will take this actual board because that's the only one I have, to be honest. It's not very difficult to remove, as you can see. Now for inputs, it's probably pretty obvious, but not sure if you can see that now. Inputs is VCC and ground as a supply voltage. Most of the signals are the interface to this display unit. So there's SPI signals, there's UART input, these are debug signals, I think. The DIO input is the D input of the latch, so the digital I/O input and output connected to the RAM. The E is the enable input that we just saw. The Q is the non-inverted output, and the NQ is Q over bar, which is inverted output. And there's a couple of grounds because we don't need much. We don't need all the pins. Now, if we stick that on the breadboard like that and apply power and lift it up a bit so you can see what's going on. First thing is a nice distracting demo mode of the display. So what the display is doing, if it's not receiving serial communication from somewhere else, is just doing a demo, just a test. This is very nice and also very distracting, so let's disable that by grounding the inverted reset pin of this display module, which we did just now. We'll focus on the DIO-latch instead. See if I can. Now let's do it like this then. That's better. And the power supply fell out. Professional video making. Yep. So anyway, what you can see here is one LED, which is the output Q of the digital I/O latch. The LED on means output is high, LED off means output is low, or 0 volts. Leftmost button and leftmost LED indicate the enable input of the latch, so I can enable the latch by pressing the button, and once again the LED on means high voltage. The enable input is high active, so high is actually active. The rightmost button controls the data input, so the DIO pin or the D pin of the latch. Right, so by pressing the button we apply high voltage at the non-inverted, at the high active D pin of the latch, a DIO pin of this module. It's just a different name. So as you could see in the, actually one other thing, the whole business with the resistor, and by driving the node connected to the RAM's IO, the RAM's data pin, either strongly by the driver inside the RAM itself or weakly by the resistor between the latch inverted output and the latch data input is not shown here. So I'm simply going to show the Q output and that's it. So what we showed on the whiteboard, you please believe that, because I'm not going to show it. So anyway, this behaves pretty much like the 8-bit latch, and that now the output Q has a certain value. Now it's on, the value is high. Now we can, I'm pressing the D button now, so I'm toggling the D input between 0 and 1, and as you can see nothing happens with the output. Now as long as and whenever I press the E button, so I enable the latch, whatever is supplied at the input, so that's the rightmost LED, is copied to the output, it's leftmost LED, right? Furthermore, like as with the 8-bit latch, exactly the same actually. If I apply a certain signal at the D input and I give a short pulse on the E input, like that, D input is copied to the E input and stays put, no matter what happens at the D input after that, once the enable signal is removed. Now this latch doesn't have a reset, because that doesn't make sense, because the value is latched every instruction cycle. There's no global reset necessary for this module. So that's basically how it works. Now thank you very much for watching, and I hope you liked it. Let me know what you think if you want. For more information please visit the qibec.org, that's Qibec.org site, about more information on the CPU and also documentation. Please watch the other videos, for example the one where a set reset latch is formed is maybe pretty interesting, because that's actually necessary in order to understand this better. So thanks for watching, and have a nice day. Goodbye.